Hi guys, got something a little bit different to look at today. Most of my videos have been about electronics projects that I've made myself, but this is just something I was investigating about the BBC Micro, which is a 6502 based computer from the 80s. And in a recent forum thread on the Stardot forums, I'll link it in the video description, there was some discussion about why when you read from certain I/O devices that aren't present in the system, you still get consistent results from the data bus, and in particular it's not the result that I expected. So just to show the computer working, it is fully functional, as you can see there. And this might not make sense to anyone who's not on the forum thread, but if we read from location FEA0, that actually reads from the network controller, but the network controller is not fitted in this machine. It wasn't fitted as standard. It's an optional extra. So when you read from that, you get 254. And this seemed odd to me because the data bus on the BBC Micro actually has pull-down resistors. There are 6K8 pull-down resistors on all of the data lines. So it pulls them down to ground. So you really ought to be getting 0 here. I thought it was interesting to look into what's causing that. And the main theory from the forum was that the 254 here is actually the hex FE from the address that it's fetching from. So the last thing the 6502 read onto the data bus before trying to read from a non-existent device was 254, the high byte of the address, and that led to that kind of staying on the data bus for an extra clock cycle, long enough for it to read it back. So something I tried when I read about these issues was actually pulling out one of the other components of the system, which is not required. It's an optional component which was fitted as standard, but it wasn't. There was a cheaper model that didn't have it, and it's one of the 6522 VIAs. And if I pull that one out, we actually get a different result. So let's have a look at that. So what I'm going to do is I'm going to remove this 6522 VIA from the system. It's an optional component. There was a cheaper model that didn't have it, although it was shipped as standard on this expensive model. I'm going to use one of this chip extractor things. I don't like these things. The last thing I'd do is wrap it around the whole chip and pull. I don't trust that at all, especially with such an old motherboard. But if I can wedge the edge of the chip extractor under the chip and between it and the socket, I can lever one end up and then the other, and I find that works quite well for removing chips from old machines, especially. There we go, that's out. So with that VIA removed, turn that back on. And now if I read from the VIA, you see we get 0 rather than 254. So it's interesting that there's a difference there. And there's a ton of other devices that aren't fitted as standard. I think A0 I showed before. FE20 is fitted as standard, but it's a write-only device. So during read cycles, nothing is really reading from that. It does have a side effect, but it's a bit of a weird one, that one. FE30 is not mapped at all in read cycles. So yeah, that's interesting. Oh, also there's a floppy disk controller at FE80, which is also returning 254 there. So all of those return 254, but the VIA is returning 0. And I thought that was interesting. My best theory as to why this is happening is that the BBC Micro actually runs at a 2 MHz system bus speed, but a lot of the devices on that bus are not capable of running at 2 MHz, so it slows the clock down when it's talking to them. And the VIAs are some of those devices. All the other ones I've used here are the Ethernet controller and the floppy disk controller for sure are 2 MHz devices, and certainly these ones it doesn't slow the bus down when it's reading those, because it doesn't actually support reading from those addresses anyway. So yeah, all of those 254 ones are actually 2 MHz, full bus speed devices, whereas that VIA is a slow device. So what I think is happening is the voltages on the data bus are decaying to 0, but they're not decaying quickly enough for the 2 MHz bus cycle to read back 0. Whereas during a 1 MHz bus cycle, it's long enough that it gets down to 0. And obviously this is not to be relied on. in the wild, you wouldn't really make anything mission critical depend upon this kind of decay. So something else I can remove is the analog to digital converter over here. Let's do that as well. Again, this was an optional component. The Model A didn't have it, but the Model B does have it. So they're all socketed in this version, so that's very handy. I can just wedge that out. This one's never been removed before, so it's a bit more difficult. The ADCs weren't used very much on these systems. I think they were good in an educational context for some, science experiments and things like that. And they were used for joysticks, but I don't have any of those, so they're just sitting here idle really. And certainly the system should run just fine without it. There we go. That actually has pretty splayed pins. I'm not sure how they got that in, but that's out now. So we can try booting up again. And so the ADC's located at FE C0, and that's returning 0. So again, the VIA is also missing, so we get zeros out of that. But all these other ones, which are fast devices, return 254. So that's interesting. So the next thing I'd like to do is actually hook the oscilloscope up that I've got over here. I'm going to hook the oscilloscope up to some of the data bus pins and just run some of these commands again and have a look at the voltage levels on the data bus during the operation. I think that's going to be really interesting. So what's the best way to do this? We're going to need a ground reference, a data pin obviously, and I'm going to trigger the oscilloscope based on the chip select pin for whichever device I'm interested in. I could use the VIA down here. I'm not sure actually, it's got 2 chip select pins. I don't know which one of those is actually connected to the relevant bit. I think the 8271 might be a better choice for that. So in order to probe this, my oscilloscope probes don't really fit into anything here, but what I'm going to do is I'm going to put these little wires, which are just offcuts from resistors. I keep hold of these because they come in handy for all sorts of things. They're small enough that I should be able to just squeeze it into the hole here, like that. It didn't go in very far, so it's not going to be a very stable connection physically. I think it'll be alright. So that's the ground pin on the 8271. I think the data pins are kind of along here, so I'm just going to take one of those here. I guess that's pin 17 or something. It's really hard to tell when it's in and when it's not. Let's try that again. That's in. That was a bit easier by hand. Next I need its chip select, which I believe is pin 24. Over here. Oops. There we go. And I want to also measure the clock, I think. I need another wire. So which is the clock pin on the 6522? Because the 8271 doesn't have a clock signal, it's a different bus design. The BBC microcircuit diagram is available online. It's fascinating. I'll link that in the description as well. Just referring to that to see where they pump the clock in. 2 megahertz E. Interesting. That's actually going to be potentially a 1 megahertz clock, I think. Oh no, that's separate. Oh, okay. Yeah, so 2 megahertz E is the one I want to actually monitor, but it's not actually going to the clock pin on the 6522. That's interesting. It's going to pin 24, which is one of the chip select pins. So 21, 22, 23, 24. Interestingly, it's the same pin number that it was on the 8271 for one of its chip selects. So we've got all those connections hooked up. Let's get the scope on. Is that on the screen? I think that's visible there. Hope the audio is not too bad as well. This scope has a bit of a loud fan in it. And I'm going to hook the yellow probe up, first of all, to the data bus pin. So I think that's probably the most interesting thing to measure. Oops. Hard to get that in without pulling the wires out. Need to make sure these wires don't short as well, that's a bit dodgy. Anyway, we're seeing a signal on the scope over there, so that's good. Oh, I've got channel 2 on as well. Anyway, that's running. There's no triggering going on here. I mean, I could... Where's the trigger? If I trigger on this thing, we should get some sort of... Oof. Well, I mean, that's interesting already, actually. I just took a quick snapshot of that signal. You can see that it went high here, and then it drifted down pretty lazily here. Then it's gone high again, and then you can see it trailing off slightly at the end of that cycle there. Let's hook up the blue line to the system clock as well. So, can you use... How am I going to get this in? Somehow I want to use the same ground and not pull them all out. And this is the 2 MHz system clock signal from the VIA. There we go, that's a pretty nice signal there. Let's get another snapshot because it's try and find a more interesting pattern on it. So it's interesting because the clock goes high. This is the phase 2 clock, so the clock goes high here, and it coincides with the rising edge on the data pin here. So I mean, the data pin came slightly late here. It's probably a RAM read. Most bus accesses will be here. So that's reading from RAM, and the RAM responded that after that kind of delay and held the voltage high. And then when phase 2 dropped again, that starts to tail off until the next cycle starts, and then it does another read, and then it tails off again. And then I guess this cycle it's returned as a low level, so that's interesting. But yeah, that's not exactly what I wanted to look at though. It is related, but we're not really looking at what's going on during an access to one of these devices that's not mapped into the system. So what I'll do is hook... I could hook up another probe for this, but I might as well just use the trigger, the external trigger on the oscilloscope for this one. So I'm going to hook that ground on again, and like I suggested before, I'm hooking this to the chip select of the 8271. Now I can switch the trigger source across to be external and do a single snapshot of that. It's not doing anything. Oh, I need to actually do a read. Yeah, okay, so the scope isn't going to do anything now until I actually read something from the floppy disk controller, so let's do that. There we go, perfect. That worked really well. So the trigger point's actually this blue arrow over here. That is interesting, look at that. So what we see on the left is very similar to what we saw before. The data bus line goes high during the clock high period. This is the 2 MHz clock, remember, and then it tails off a bit, before the next clock cycle starts. And generally speaking, things aren't going to be writing stuff to the bus during the clock being low. Certainly the RAM won't be, because it's doing the video access during the clock being low, so it's just not available to the CPU at all. Ooh, that explains a bunch of things. Maybe. Huh. I'll explain that more later. I think I have another theory now. Anyway, it looks like we're reading, whichever data pin this is, we're reading high, 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 then low on the next bus cycle, and then high again, and you can see it dropping off each time at about the same rate here, until the next bus cycle starts. But what happens over here, where the trigger is actually set, this trigger is triggering on the rising edge of the floppy disk controller's chip select line. And that's actually a bit late. I mean, that's the end of the bus cycle in which it's being accessed. But never mind that. You can see what actually happened here is it's got a really droopy kind of intermediate voltage level that it's presenting to the CPU. Now, the rising edge of the chip select, or rather the falling edge of the clock cycle in which it went high, is probably this one that it's actually reading the data at. I'm not sure actually. So one thing that's really confusing here is that somehow what I was expecting to see was that it would be high and then it would sort of drift off in a continuous curve while the actual access takes place here. But it's not really doing that. It's actually going low and then somehow it's going back high again, and it's going high to about the same level that it tailed off at before. So that's really quite confusing. I'm not totally sure what is charging the data bus up to that level instantaneously at that point. Something must be driving it. Oh, I said I had a theory earlier on about what was going on here. So my theory is that this could be related to the way the video circuit has access to the RAM for half of the cycle. But that doesn't really make sense. No, I don't think it could be that. The bus preloading would be much more random if it was the video circuit. It's very odd though. Something is charging the bus up suddenly here, and it's not a normal sort of RAM read, because the RAM reads look like this. Yeah, that's pretty odd. We can look at that more closely. It's very interesting anyway. Let's make the trigger be on the falling edge and do another capture. Okay, so that's now triggering on the falling edge. So, yeah, this point here that I've lined up on the axis is the start of the 8271 floppy disk controller being asked to output data, and the opposite edge was actually at the next rising edge of the clock. So it's this point here where phi2 falls. That's the point where the CPU actually samples the voltage on the bus. So the other question is what's going on during 6522 read, where it's reading zeros. And I think what would be happening there is, because of the way the clock stretching works, actually I could... it's not easy to demonstrate that. What can I do? I know. If I trigger based on... I have to do this very carefully to avoid shorting it. If I trigger based on the 6522's other chip select line, let's try reading from the 6522 now and see what that looks like. Nothing. What have I done wrong? Oh, didn't tell it to go. Let's try again. That's nice. So this is what happens with the elongated clock. And it's really interesting because you can see how the BBC Micro extends the clock during these slow bus accesses. There are actually two profiles for this, and it depends how the parity is of the 2 MHz clock versus the 1 MHz clock during the operation. But what it's done here is that the trigger point is again on the axis here, and I think the way it's rigged up, you won't see it on this clock signal, but I think it's this falling edge of the phase 2 clock here, which is used to trigger the 6502 to actually read the data. So this has now fallen down so low that it's virtually zero at that falling edge there, and that's why we're getting a zero from reading these slow devices that have a much slower clock signal. I'm going to run that one again because there are 2 patterns to this clock, and I'd like to see the other one. It might not show up on this one actually. No, I don't think it's going to show up. Yeah, this isn't the CPU clock. This is a sort of in-between clock. The CPU clock has a slightly different shaping to it to balance out the cycle more. Anyway, that's really interesting. So looking at the bus voltage line here again, you can see all of these highs and then a low. I don't know exactly what it's doing here. Probably depends which bit of the data bus I'm actually monitoring here. It's just whatever it was doing on the instructions leading up to reading from this memory address, also with this I/O port address. But again, we see it fall off here, and then we see it go AWOL for quite a long time, and then all of a sudden it comes back at the same voltage level that it was at before and decays the rest of the way. So yeah, that's probably all I'm going to be able to figure out at the moment. I'm at a bit of a loss to explain why it's jumping back up here. I'll have to refer to the circuit diagram, and I'm going to put a link to the circuit diagram in the video description if you guys are interested in having a look at that and seeing if you have any theories as to why we have this long period of zero on the data bus. I'm sampling straight from the data bus here at the floppy disk controller, and you know how that's jumping back up. Something must be driving that bus back up again. My little theory earlier on was there's a transceiver between the CPU data bus and the RAM data bus, because the RAM data bus is kind of in my VGA circuits is what I call the video data bus. In the BBC Micro, the RAM and some of the video hardware is all kind of on that side of that transceiver, and that's actually the main system RAM as well. There's no distinction on the BBC Micro, but it is on that side of a transceiver, and that does mean that potentially, if that transceiver was turned off and then turned back on again here or something like that, the transceiver could be... No, that doesn't make any sense either. No, I'm at a loss to explain why this shape is just bizarre. So if you have any theories, let me know. I'd love to hear them. Make it bigger. Anyway, I hope that's interesting. Again, not my electronics. This is off-the-shelf electronics, but it's something I'm very interested in. It's what I grew up using. It's what got me into computers in the first place when I was a child. Very close to my heart. I was thinking of doing more videos about it. One of the videos I was thinking of doing was potentially like trying to develop a video game in 6502 assembly on this machine, using nothing but what comes as standard in the machine. I think that would be a really interesting thing to try and do, because I've never actually done that really before. I've dabbled a bit with assembly on this machine, but not really made anything substantial. But yeah, let me know if you think that would be interesting. I'm not sure whether I'd put it on this channel or on a secondary one or something like that, because most of the stuff I do is electronics, and that is very much software, which might not be to everyone's taste. We'll see.